everyone. Today we're going to go over Chapter 2, Measurement and Problem Solving. The thing I want to tell you is that in a measurement, your last digit is your estimated digit. It's your uncertain digit. So in this particular situation, it says average global temperatures have risen by 0.6 degrees Celsius in the last century. So basically what that means is this last digit was estimated here, so it could have risen 0.7 or it could have risen 0.5. So we just know that we're plus or minus 0.1 on that measurement. Scientific notation. Scientific notation is a way to write a really large number or a really small number in a much more compact way. So in scientific notation, you're going to have the decimal portion. Let's go back here. You're going to have the decimal portion, and then you're also going to have the exponential portion. Okay. A positive exponent, all right. A positive exponent means that you're going to have a number that's greater than 1, and a negative exponent means that you're going to have a number that is less than 1. So if you see here, 10 to the first equals 10, so we have a number greater than 1 here. And 10 to the negative 1 means you have a number less than 1. That's 0.1. Okay. All right, so when you are converting into scientific notation, basically what you're going to do is you're going to look at the number that you have, whether it's a really large or really small number, and you're going to move that decimal to the right of the very first non-zero digit. So in this number here, 5983, I know that I'm going to want to have my decimal here in this place. Okay, so I need to look and see how many places I had to move it over. So in this situation, our decimal, our assumed decimal is at the end, and we'd have to move it 1, 2, 3 places to get it there. If you're moving your decimal point to the left, you're going to have a positive exponent, but also a good way to remember is that you know that this number is greater than 1, so you're going to have a positive exponent. And our answer becomes 5.93 times 10 to the positive 3. And it's 3 because that's how many places you had to move the decimal over. This one here, we have a number that is less than 1. Okay, so our decimal is right here. We need to move it to after the first non-zero digit. So we have 1, 2, 3, 4 places. Since I moved the decimal to the right, I'm going to have a negative exponent, but also we know that that number is less than 1. And so that also means that you're going to have a negative exponent. The answer becomes 3.4 times 10 to the negative 4. All right, let's take a look at a number here. So remember, your last digit is your estimated digit. Okay, so this one here is estimated. The first 4 digits are certain. The last digit is estimated. The greater the precision of the measurement, the greater the number of significant figures you're going to have. Okay, so the more significant figures that you have, that means that you have a better measurement, a stronger measurement. About this measurement of this powder on the scale, you can tell here that the scale, if you see here, it starts at 0, and then there are tick marks for every gram. Okay, so we start at 0, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. Okay, so we definitely know that the measurement of this blue powder is at least at 1, but then remember, when you're doing a measurement, you always have to estimate 1 digit farther than what you can see. Okay, so this powder here we know is 1 gram, but now let's estimate what the rest would be. So I can tell it's definitely between 1 and 2 grams, and to me it looks like it's a little closer to 1 gram than it is to 2 grams. they came up with 1.2. This 0.2 is their guesstimated, their estimated digit. I would say that's probably close to what I would guess too, is 1.2. But you know, you could probably look at it and go, well, maybe that's 1.1 or maybe that's 1.3. But you're just kind of eyeballing and guessing that last number. So you're always going to, in a measurement, you're going to estimate one number past what you're able to see. All right, now let's talk about significant figures. How do you count them? How do you know what is significant? All right, all non-zero digits are significant. This is supposed to say 26, but it's a little bit sloppy. These writing pens are not the best. So this has two significant figures. Interior zeros, so that's zeros that are between two numbers, okay? So they are significant. So this 0 is significant, so this here would have 3 significant figures, okay? Trailing zeros, zeros to the right of a non-zero number that fall after a decimal point are significant. Okay, so here 26.00, because there's a decimal point here, these are all significant. So this would have 4 sig figs. Okay, trailing zeros that fall before a decimal point are significant. Okay, so let's say we have a number that is this 2600 and they have a decimal point put there. These zeros would be significant. Okay, so this would have 4 significant figures. All right, leading zeros. Zeros to the left of the first non-zero digit are not significant. They only serve as placeholders. They just tell you where the decimal is. So these guys here are not significant. So this here would only have 2 significant figures. Trailing zeros at the end of a number, but before an implied decimal point, are ambiguous, so you should avoid them. So what they're saying here is that, you know, we don't really know how many significant figures this number has. Probably what you'd want to do is put this in scientific notation and make it like 2.6 times 10 to the 3. So you want to kind of avoid, if there's not a decimal point, you want to avoid a bunch of zeros after a number. Right, exact numbers have an unlimited, let's go back, have an unlimited number of significant figures. Sometimes you'll see when you have a measurement, it'll say exactly. All right, exact counting of discrete objects. Okay, so I can say there are 29 people in this class. Okay, integral numbers that are part of an equation. And defined quantities are exact. So some conversions will say that they are exact. So like generally if you have like an English to English conversion, like 12 inches in a foot, that would be considered exact. But if you have, say, English to metric, sometimes it'll tell you that it's exact. How many significant figures are in each of these numbers? 0.0035, these leading zeros, they are just holding the place of the 3 and the 5. So there's just 2 significant figures here. Okay. 1.080, because of this decimal point, there are 4 significant figures. Okay. 2371, all are significant. 2.9 times 10 to the 5th, this is actually a typo. This is actually 2 significant figures. These guys here are significant. This is a defined measurement, okay? So this is unlimited significant figures. And 100.00, because of this decimal point here, all of these are significant, so this is 5 significant figures. And this one, there's no decimal point in it. I mean, we know that there's a decimal at the end, but it's not written there. And so this has an ambiguous amount of significant figures. Figures and calculations. Rules for rounding. When numbers are used in a calculation, the result is rounded to reflect the significant figures of the data. Okay, your answer can only be as strong as your weakest measurement. For calculations involving multiple steps, okay, round only the final answer. Do not round between steps. That will cause you some problems and probably some errors. Rules for rounding are basically the same rules that you guys have known all along. You guys are going to be looking at your first non-significant digit, and if that first non-significant digit is greater than or equal to 5, you're going to round the last significant digit. If that first non-significant digit is less than 5, you're going to leave that number off and all that follow. Okay, we'll do some practice here. Oops, that one went really fast. So for multiplication and division, like I say, when you're doing rounding, your answer can only be as strong as your weakest value. So we have to look at what it is that we're multiplying. So we look at this first one, 5.02. This has 3 significant figures. 89.665 has 5 significant figures, and 0.10 has 2 significant figures. Okay, since our weakest measurement only has 2 significant figures, our answer can only have 2 significant figures. So when you multiply all of these together, what pops out into your calculator is this whole number here. But because our weakest value only had 2 significant figures, we know that that's this number here. Okay, we do have to see if we need to round it. So this goes back to what we were talking about on the previous page, our rules for rounding. You're going to look at your very first non-significant digit, and if it's greater than or equal to 5, then in that case you would round this 5 up to a 6 and leave all of the rest of these numbers off. Okay. If the number is less than 5, which it is, we don't do anything with this number here. We just leave it a 5 and leave all of the rest of these numbers off. Okay, so because this is a 0, this just stays 45. Let's try another. Oops. Division is the same. So if you were to divide 5.892 divided by 6.10, what's going to pop out into your calculator is this whole thing here. Okay. And but I know that I can only have 3 significant figures because my weakest measurement only has 3 significant figures. So that's these 3 here are significant. You're going to look at your first non-significant digit here and see if it's greater than or equal to 5. If it's greater than 5, then I have to round this guy up right here and then leave the rest of the numbers off, which is the case. Okay, so the answer becomes 0.966, okay, because of rounding. If this, let's say this answer was 0.96510, okay, then I would look at this and I'd go, okay, well, this is a 1, which is less than 5, so then the answer in that case would be 0.965, okay. All right, let's look at the next one. Oops, I just went too fast. Okay, addition and subtraction, you're going to go by decimal places, okay? So whatever you're adding or subtracting, the one with the least amount of decimal places represents how many decimal places your answer will be carried out. All right, so if you look at this here, this guy goes 2 places past the decimal, this goes 3 places past the decimal, this goes 3 places past the decimal. Because this one only goes 2 places past the decimal, my answer can only go 2 places past the decimal. So what pops up in your calculator is 9.214, but it's going to just be 9.21 as my answer because it can only go 2 places. And I know I don't need to round it up because my first non-significant digit is a 4 and not a 5 or higher. All right, let's try one more. 4.8 minus 3.965. My answer can only go 1 place past the decimal because that's what my weakest value goes. Okay, so what comes out in your calculator is 0.835. This is a 3, so I'm definitely not going to be rounding up the 8, so my answer just becomes 0.8. All right, we'll do more in the next video. Awesome job.